Le Chatelier's principle says, if a system at equilibrium is disturbed by a change in temperature, pressure, or concentration of a component, the system will shift its equilibrium position to counteract the effect of the disturbance. Let's start with a non-chemistry example. Let's say that it's raining and we're in our boat. Our boat is filling up with water, and so we're bailing. And we've got a nice rhythm going. Bail, water, bail, water, bail, water, bail, water. And we notice that while the water level in the boat isn't going down, it's not going up either. In other words, we're at equilibrium. The rate at which rain is coming into the boat is equal to the rate at which we're throwing water out of the boat. We keep that up. Bail, water, bail, water, bail, water. We've set up some sort of an equilibrium system. Suppose now the rain stops and the sun comes out. What are you likely to do? You're probably not going to bail as fast anymore, because you realize that, oh, the system has changed. I don't have to bail water, bail water, bail water. I can bail water, bail water. I can take it a little easy. On the other hand, if it suddenly starts really raining, what are you likely to do? Bail faster. Similarly, chemical systems, when we change something, they will shift to alter their state of equilibrium. Let's start with a change in concentration. This reaction at the top of the screen is called the Haber process, developed by Fritz Haber. And let's assume that this system is at equilibrium. Reactants are turning into products, and products are turning back into reactants at the same rate. Suddenly, we decide to change something. We decide to add more N2 into the system. You can imagine the system. If we personify the system might look around and say, wait a minute, where did all this extra N2 come from? I liked it the way it was before. I better get rid of some of this N2. And the way you get rid of added nitrogen is you shift away from it. You consume some of that nitrogen and produce more of what's on the product side. So we would say shift right. Let's take a separate case. The system's at equilibrium. It's happy, you might say, in its state of affairs, and suddenly it looks around and says, wait a minute, where did all this hydrogen come from? Holy cow, I got to get rid of this. Shift right. Use up some of that hydrogen and produce more product. If we took, for example, a different case where the system's at equilibrium and we added more NH3. Again, you can imagine the system thinking to itself, of course it can't think, but it happens like this, the effects are the same. Where did all this NH3 come from? We got to get rid of some of this. Well, which way do you shift to get rid of all this extra NH3? You shift to the left and produce more reactant. Suppose we have a system at equilibrium and we start taking something out. In this case, let's say we take some NH3 out. Take NH3 out. Take NH3 out. Pretty soon the system says, wait a minute, aren't we short some NH3? I thought we had more earlier. Shift to the right. This is what happens anytime you add or remove a substance from an equilibrium system. The system is going to shift. If you add a substance, the equilibrium is going to shift away from that. If you start removing a substance, the equilibrium is going to shift towards it. Here's what happens, for example, if we add H2 to this Haber process. First of all, if you look at the equation at the top of the screen, when we add hydrogen, clearly we're going to shift to the right, and we're going to establish a new equilibrium system. We could kind of show that with this diagram here. Here we have the original equilibrium. Time is on the horizontal axis. You can see here initially that the amounts of these three things are not changing. Suddenly, we add more hydrogen to the system. You can see that the hydrogen amount spikes up. When we then shift to the right, that means we're going to try to use up some of the hydrogen. So the hydrogen amount, you can see in the graph, drops a bit. And the nitrogen amount will drop somewhat as well, because some of that's going to be used up. The NH3 amount is going to increase somewhat. There's going to be a certain amount of time over which we establish a new equilibrium. And then we will have established a new equilibrium. And you can see at the end that the amounts of those things, again, are not changing. We have a new equilibrium state compared to what we had before. What about a catalyst? If we add a catalyst to a reaction, the forward and reverse reaction rates are both increased, but there is no net shift in the equilibrium position. So you could shift left, shift right, or no shift. Or, as I like to say, duh, no shift. Like someone says, hey, you know, I think the Alabama football team looks like it might be pretty good again this year. Duh, no shift. That's what happens whenever you add a catalyst. A catalyst will increase the rate at which equilibrium is achieved, but the final composition of the system is unchanged, as is the value of the equilibrium constant. Let's summarize. Le Chatelier's principle states that an equilibrium system that is subjected to any stressor will tend to shift to a new equilibrium state in attempting to offset that stressor. In terms of concentration, if the stressor is the addition of a reaction component, the equilibrium will shift away from the added component. If the stressor is the removal of a reaction component, the equilibrium will shift toward the removed component. The new equilibrium state is generally not the same as the original state. The addition of a catalyst speeds up both the forward and reverse reactions with no net shift in the equilibrium position.